Hello, good evening everyone. Thanks for sticking out with me and staying till the end, because I'm the last speaker of today. So today I want to talk to you about a topic very near and dear to my heart, which is testing. And if you think about it, there's like plenty of resources available online which talk about how to write clean code, how you should organize your code, and so on. But the same doesn't quite exist for testing, right? So that's actually what I want to cover today, and we're going to cover some basic ground rules, and then we're also going to look at actual tests and see how we can optimize them in practice. So before we get started, maybe a small word about myself. So I'm Jeroen Mols, I'm Belgian actually, and I work for Philips Hue. I'm the lead Android developer for the Philips Hue app. We're hiring, by the way, and I'm also a Google developer expert for Android. So without further ado, this is what we're going to cover today. So we're going to cover some basics, some core principles, a few ground rules, and then I really want to talk about what is code coverage, what does it mean, same for TDD, and then debunk some common testing myths, and then we're actually going to dive in some code, take actual tests and see how we can optimize them and make them better. And then the last section is like an aggregation of stuff I learned over the years and that I would like to share with you. Okay, so first of all, the core principles. Why do we actually write tests? There's actually many reasons. You do it to make sure that the code is doing what it's supposed to do, but also to make sure that the code keeps on doing what it's supposed to do. Plus, tests could also serve as a form of documentation. There's a big caveat there, because you really need to think about how to write your tests so that you properly document your code, but you could use it in such a way. Further, tests also enable you to refactor. Because if tests are in place, you can just change the way your code looks or the architecture of your code. You rerun the test, and you still know that it's behaving the way it should behave. Plus, it enables you to release faster. Writing unit tests is also the easiest form of testing. But if you really, really think about it, the only reason why we write tests is to run them. Because if you don't run tests, you won't get any value from them, right? Now, testing is always a long-term commitment. Because if tests fail, you're going to have to go and fix them. If, tests become obsolete, you need to delete them. If your code changes, you need to change your tests. There could even be bugs in the test, just like with any code. So you really need to consider test code as production code. It's no different than all other code that you have in your project. We're going to see a bit later on that slightly different rules apply, but it's still production code. And tests require infrastructure to run. So you need to have a CI to run all of your tests and to see if they're still passing. You maybe need a mocking framework or dependency injection framework, probably some other frameworks to be able to properly test. You also need to have a build command in order to actually run all of those tests, maybe Slack integration when tests fail. And what all of these things actually help you do is optimize your tests for failure. Because in the end, as long as tests pass, everything is fine. But when they fail, that's when we really need to take action and go and fix it. So we also want to optimize them for that case. So now that we have the core principles, what are actually the 3 ground rules that make tests really awesome? First and foremost, tests need to be fast. Not just super fast, but really ludicrously fast. And that is because tests make sure that your code is doing what it's supposed to do, and that it keeps on doing that over time. But tests can only do that when they run, right? So every time we run our tests, we're going to get a piece of feedback. And we want to have rapid feedback. Because I don't know what code I wrote 2 days ago, but I still know what code I wrote 5 days ago. So that means that you don't want to run your tests like once every release, not just once every day. You really want to run them after every meaningful code change. And if tests are slow, it's going to take a long time for them to run. And if it takes a long time, you're not going to run them often, and hence you're not going to get much value from it. So it's like a vicious circle. You need to optimize your tests, make them as fast as you can possibly get them, then you will run them often, and you will get more value from them. This has consequences. Because it means that we can't do any sleeps in tests. We can't do any waits. We shouldn't do any of those things in tests. That's just way too slow for a unit test. It also means that we cannot run tests against a database, file operations, hit a REST endpoint. No, all of those things, they don't belong in a unit test. Similarly, if you're an Android developer like me, you shouldn't run your tests on an Android device, at least not your unit tests, because deploying those tests is simply too slow. So tests need to be ridiculously fast. They also need to be small and focused. By small, I mean physically small. If you look at a test method, it should only be a few lines of code, so that when you look at it, you can immediately understand what's going on. They also need to be focused, because what would you prefer? So imagine if there is a bug in your code. What would you like to have? That only one test fails because of that bug? Or that like 5 or 10 tests fail because of that bug? The first one, right? You want to have only one test failure for every bug. So your tests need to be focused and only test one specific part of your code. And then when the test fails, yeah, you want the name to clearly indicate what the problem is. So look at this example. This is a good example of a really good test. It says, login should fail when the password is wrong. So imagine if this test fails, yeah, in the output you're going to see the name of the test method, and you're immediately going to know what's going on. And then the last rule for awesome tests is they need to be 100% reliable. Seriously, you cannot tolerate any flakiness. Because imagine if tests fail on your CI server. Then the very first thing you have to do is go to that CI server and fix those tests. Of course, because if your CI is failing, you can't integrate any new code, right? So it doesn't make any sense to work on features anymore. You need to go and fix that build. But imagine if you go and analyze a build, you don't immediately find a problem, you just look at it for a few hours, you scratch your hair a few hundred times, and then suddenly you don't know what's going on and you just rerun the test and boom, suddenly they pass. That's frustrating, right? Imagine doing that 2 times or 3 times. It's going to drive you nuts. And what that's going to cause you to do is, over time, whenever a build fails, you're not going to care anymore. You're just going to assume, yeah, it's going to be a random failure again, so I'm just going to wrap up my feature and we'll take care of that later. So what you're actually doing is you're losing your trust in your regression safety net. And yeah, if you don't trust the test you write, why are you writing tests in the first place, right? So you cannot accept any flakiness in your tests. Now, have a look at this test. It's a very simple test, actually. So what we do here, we just want to format the date and time to be able to log it or write it to some backend, doesn't really matter. And what this test does is, it first calculates what the output should be, and then we actually ask our time formatter to calculate the output for us. Well, if you run this test, it's going to pass. I'm sure of that. But this is actually a flaky test, because the first line, expected time, creates a new date object. And internally in the time formatter in the second line, also a new date is generated. So both of those methods get executed with a slightly different date. And now lines of code execute blazingly fast, so it only takes like a few nanoseconds to execute them. So the times are going to differ by nanoseconds. And we're actually checking if the date is properly formatted up to millisecond level. So 9 out of 10, or maybe even more times, this test is going to pass. But this one time, or these few times, it's just going to be the first line is going to take a date at the end of 1 millisecond, and the other time is going to take a date at the beginning of a new millisecond, and then this test is going to fail. So the way you fix something like this is not rely on the date to be internally generated, but share the date between both invocations. So if we feed the time formatter with the current time, then suddenly this test is stable, because both of them use the same time. Now, if you don't want this artifact on your API, that's actually in Kotlin very easy, because you have default parameters, and you can just assign a default value to the now parameter. OK, code coverage. Let's make stuff a bit more interactive. So imagine you have an app which has 100% code coverage. I know, it's a stretch. It's very hard to get to 100% code coverage. But just let's do the thinking exercise. Your app has 100% code coverage. Can that app still have any bugs? Who here thinks that if you have 100% code coverage for your app, that the app is bug-free? OK, nobody. That's excellent. And you're right. because there could be like these tiny little bugs which aren't like critical to success, like text being a pixel off or having the wrong color or UI inconsistencies. You could also have the interplay between classes. So classes communicate with each other and maybe there's goes something wrong there. And thirdly, yeah, you can have external data that corrupts your app, right? If users enter data into an edit text field or your backend returns some random response, your app could also have bugs because of that. But if you have a class, just one single class in your business logic, if that one has 100% code coverage, then surely it cannot have any bugs, right? Who thinks that if a class has 100% code coverage, that it cannot have any bugs? Are you just all sleeping, or you really already know the answer? So let's investigate an example. This is a simple calculator. We write a test for it. So 1 plus 3 should equal 4. This has 100% code coverage on every level, by the way. Class, method, line, doesn't matter. Now, what if we change the test and we remove the assert? What is that going to do to your code coverage? It's going to say the same. Because code coverage just checks whether a line is touched during a test or not. It's not smart enough to analyze if you're actually doing a meaningful assert. So code coverage is really meaningless. But it's even worse than this, because we can also change the implementation of the calculator. If the calculator now hard-coded returns a 4, then still this test passes, we have 100% code coverage, but surely we don't have a useful calculator, right? So 100% code coverage does not mean anything. It's completely agnostic about the quality of your tests. It doesn't check any functional coverage. It doesn't even check that you have any asserts. And it's even worse than this, because let's imagine that code coverage is actually a meaningful tool, that actually tells you that your tests are high quality. Let's assume that for a second. Even then, trying to strive for 100% code coverage would not be a good idea, because adding coverage in the beginning of a project is super easy. Some stuff is really easy to test. But other stuff is nearly impossible to test. If you have thread swaps in your app, moving from one thread to the other, or you have UI, or you hit databases, web services, how are you going to unit test that? You can actually test everything. But at some point, you're just going to invest so much time and effort in trying to get a test that kind of works, and then you end up with a test that's nearly impossible to maintain. So what are you really gaining? So even if code coverage would be a good tool, then still 100% code coverage would be a useless goal. And then you may be asking, like, but what's the deal with code coverage? What is it useful for? Well, actually, it's a good tool to basically double-check that you're doing the right thing. If you, with your team, are doing good engineering practices and you're serious on testing, then code coverage is a great tool to be able to check that you're doing the right things and that everything is moving in the right direction. Because if you make a pull request and the code coverage for the pull request is 0%, yeah, surely there's something wrong with the pull request, right? And adding code coverage to your pull request is also some kind of gamification. You can actually see the code coverage going up. You can comment each other and like, yeah, be proud of each other in the team that you're actually doing this. So code coverage is really a developer tool. It helps you and your team basically gamify your work and check that you're doing the right thing. So I hope that I managed to convince you that should anyone in your organization ever ask you to increase code coverage, that you just go online, you download a tool which can generate tests even for all of the if statements. It's like 30 minutes of work. You run all of your tests, you will have 100% code coverage or very close to it. You claim your bonus, and then you can just continue doing the actual engineering that you should be doing. All right, test-driven development. Who here knows what test-driven development is? Ah, so you are awake. Then you must just be smart. And who here uses test-driven development on a daily basis? That's a bit less, but that's still okay. So test-driven development is all about the premise that you write your tests before you write your code, right? Which actually begs the question, when should you write tests? Should you do that before or after you write the code? Well, honestly, I don't care. It doesn't matter. As long as it works for you and as long as you write tests, then I'm already happy. But if you write your tests before you write your code, there's actually quite some interesting advantages. Because, yeah, if you first write a failing test, you have the guarantee that the test would actually fail. It reduces the manual testing, because you're actually already verifying your code with the tests. You don't have to do that manually. It's usually also easier, because then your tests also influence the design of your code. It forces you to think better about the requirements. So if you're writing test first, you become a lot more aware of like, hey, can this parameter be null? Can it be empty? Can it be this? Can it be that? So you're going to get more into the flow of actually thinking about those edge cases. And it also helps you split the problem in smaller parts. But I'll get back to that later. So what is TDD actually? It's an extreme way of working. And I say extreme because it really requires a lot of patience, a lot of persistence to force yourself to work according to like a fixed principle and a fixed set of rules. Those rules are actually quite simple. You shouldn't write any code except if you write it to make a test pass or to create a new failing test. And if you write code to make a new failing test, you should write the bare minimum amount of code to get to the next failure. And if you fix a failing test, you should do the same. Write the bare minimum amount of code to make the test pass. And this will actually push you into a nice little flow called red-green refactor. So you'll first write a failing test, you run all of your tests, then you fix the test, you run all of the tests and verify that they're passing, and then you see is there anything I can refactor, and you run your tests again. Do you see how often you run your tests? That's why it's so important to have super fast tests. If you don't have fast tests, TDD, yeah, simply cannot succeed because nobody has the patience to wait for 30 seconds on every code change, right? This workflow actually also has some other advantages. It's a very rewarding experience. You see your tests always increasing. You see them becoming red and then green, and it's satisfyingly pleasing to work in this way. And if somebody comes to your desk and interrupts you, then all you have to do is just tell them like, hey, wait a minute. You work further till you reach the next failing test, and then you can always stop your work. You can go and have a meeting for 30 minutes, 10 hours, 10 weeks, doesn't really matter. But if you then come back to your code, all you have to do is rerun all of your tests, you see where it fails, and then you can just pick up your work from there. That's, by the way, also a great way to leave the office in the evening. You just stop with the failing test, and the next morning you can very easily pick up your work again. So, test-driven, if you do some research about it, then either people are talking about test-driven development or test-driven design. And actually, both of them are true, and in my opinion, the D can stand for a lot more things. So yeah, sure, it is development, because you're actually writing code. It's a way of writing code. It's also design, because when writing tests first and forcing you to refactor at very small increments, you're going to end up with pieces of code that you would never have imagined if you would have tried to write it in the first place like that. So TDD really results in very nice and clean solutions. But it's also a way to divide and conquer. What if you have a very big problem to solve? Then you might be a bit puzzled like, whoa, gosh, how on earth can I start working on this problem and fix it? Can be hard, right? But surely you can write like a very simple test that fails to start working on the project, right? And then you can just build it up from there, and before you know it, you have the entire feature implemented. It's also a way of documentation, because if you follow TDD strictly, then you actually will have documented your train of thought in tests, and you can just run over it again and then see what you were thinking at the time when you wrote everything. It's DevOps, because if your tests don't run fast, TDD is impossible. It's determination, because it's a very extreme way of working. You really need to force yourself to do the red-green refactor. You need to force yourself to follow those basic rules. Because typically, as programmers, when we get a new problem, we enthusiastically want to start solving it and writing the code, right? And TDD is counterintuitive in that sense, because TDD says you should start with the test first and then write the code. And if you first prototype something, you have to throw it away and then start with the test first and redo it all over again. And test-driven is also a dream. It doesn't make any sense to try and do everything in an app DDD. That doesn't really makes no sense. You should use it where it's useful. And for instance, like if you're developing UI, yeah, then it's not useful, right? So use the tool for the right job. Don't like strictly stick to it. Let's have an example of DDD. So we're gonna develop a calculator. So we start with a test, obviously. And the first test we're gonna write is can instantiate. Now at this point, the calculator class doesn't exist yet. So we get a compiler warning. So we just do Alt-Enter in IntelliJ, and it generates the class for us. OK, we run the test, they pass. Can we refactor something? No. Next step, we write our first test. 1 plus 3 is 4. So the sum method doesn't exist yet, so we'll have to generate it. Again, Alt-Enter, and we're really deriving the code from our test, you see? So we implement the method. Now we run our tests, and they fail. OK, good. Let's implement the test. What is the bare minimum amount of code you have to write to fix those tests? Just return a 4. So return 4. Is there now anything we can refactor? Well, in the calculator class, no. But in the test class, actually, the can instantiate has become redundant, right? Because that's also implicitly tested by the next test. So let's remove that one. Let's add a new test. 2 plus 3 is 5. Let's run it. OK, it fails. Let's fix the test. And the simplest way to fix that is just add an if-else statement. OK, we run the test. Everything is green. Can we refactor something? No. Next, we add a new test. 3 plus 3 is 6. OK, let's implement the code for that. This really starts to look very nasty, right? But anyway, we don't care. We run the tests. They're passing. All right, good to go. Is there now something we can refactor? Yeah, maybe we can simplify this to A plus B. Let's try it. We run all of the tests. They all pass. Boom. We've written our simple calculator. So this is really the flow you need to stick to. You notice that it's like very involved, very verbose. You need to like constrain yourself to stick it to the mode. But if you do that, the end result is really worth it. So, some testing myths. Testing slows down development. Yeah, it's true. Surely writing tests takes more effort than not writing tests, right? But there's actually also some interesting things to remark there. Because if you write tests, you save on manual verification. Because the tests are actually, they already verify that your feature works, so you don't have to try and manually verify that. So you save time there. And over time, your test can also keep on checking that everything keeps on working. So you win more and more time over time. So what basically happens with tests is, instead of starting super fast and then slowing down, tests force you to start at like a maintainable, sustainable pace, and you can continue to sustain that over time. So after a while, you'll actually get a benefit from writing tests. But initially, it definitely slows you down. Testing is hard. Is writing code hard? No, not really. After so many years, you've gotten used to it, right? Surely you have big problems to solve in your app, and it can sometimes be complex. But writing the code itself, I think for most of us, isn't a problem anymore. But do you remember when you started writing code? When you had to learn Git and Jenkins and the language and the tool and this and that? That was quite overwhelming, right? It's the same with testing. Learning something new always takes time. It's never easy. But once you get a hang of it, it becomes your second nature. And with testing, there's an extra effect into play. Because if you have a legacy code base, which wasn't set up to be testable, then testing can be extra hard. But even there, you need to learn a few tricks, like how to mock, how to inject dependencies, and so on. And once you get a hang out of those tricks, then also that becomes a lot easier. Test code is not production code. Well, we already established this, right? Test code is production code. Because what are you going to do once you've written all of those tests? Are you going to toss them away when the feature is complete? No, that would be insane, right? You're going to keep them. And if you're keeping something, you have to maintain it. It's as simple as that. Simple code shouldn't be tested. No. Actually, the simplicity of or complexity of the code has nothing to do with the fact that it should be tested. The only thing that influences that is the amount of effort it would take you to write the test versus the benefit you would get out of it. There's plenty of examples available of rockets exploding or Mars landers crashing on Mars due to like a very simple arithmetic error, a conversion from standard units to metric units or the other way around, which could have been prevented with some basic tests. So this for sure isn't true. Testing negatively impacts production code. Yes, it does. Testing does impact your code, because testing typically forces you to have more layers, because those layers allow you to inject dependencies, and then in such a way you can test your app. Plus also, if you have a legacy code base, and sometimes you need to open up stuff to make it testable and stuff like that. So you really do have some artifacts from testing on your code. But on the other hand, testing also forces you to do quite a few good things, because large classes are very hard to test. So tests force you to have smaller classes. If you don't inject dependencies, you can't mock them. So tests forces you to do dependency injection. If method names are bad, then if you look at the test and you want to understand what's going on, it doesn't make any sense. So it forces you to write better test method names or method names. And if you use TDD, well, you get less code overall. So test also has a lot of positive impacts on your code. And if you then think about the time you save of doing all of the dull, repetitive testing work by hand, then for sure, the impact is more than positive. And then the last one, everything should be tested. Again, this isn't true, it's just plain wrong. You have to balance the benefit versus how much effort it takes you. But what you shouldn't be doing is let the decision of what you're going to test or not test, to let that depend on how you feel that day. If you're tired, saying like, "Ma, I'm not going to write tests," and if you feel good, then you're going to write tests. That's something you shouldn't be doing. You should, as a team, set a clear directive, a strategy. These are the kind of things we're going to test. These are the things we're not going to test. Fine. And then you just stick to it as good as you can. So let's actually analyze some tests and see if we can make them better. This is the first test. Please all have a look and think about for yourself what you can improve with this test. So if you look at the test, we're actually inheriting from test case, and we're prefixing our test with test underscore. So our test method starts with test. This is no longer needed anymore. This was JUnit 3 syntax, and we can actually just make it JUnit 4 syntax, and all you have to do in JUnit 4 is slap a test annotation on the method. Next, we also have this custom test runner at run with. Okay, given this is an Android-specific thingy, and I know most of you aren't Android developers, but this one is actually also not required, because what this one does is it allows you to mix and match JUnit 3 and JUnit 4 tests in the same file, which you shouldn't be doing in the first place, so then you don't need this one. Plus, this also seems to suggest you're going to run this kind of test on an Android device, which is plain overkill, right? Because it's a calculator. You don't need to have access to the OS to run that test. So let's also strip that out. So now it's our test, nice and clean. So the first tip is always use JUnit 4 syntax. Let's make it a bit more interesting. This test already looks quite a bit better, right? What's wrong with this? Actually, it seems okay-ish, but this doesn't quite scale. Because if you now look at the login as failed method, then you don't know how the web service is created. And okay, you can just look a few lines up and then see that the web service is created in the setup method. But this doesn't scale quite well across the fault, right? If you have multiple tests in your class, and this login as failed method is like on the second page, then you always have to scroll up and down to be able to see what's going on. So it's actually better not to use the setup method and to just put this code directly in your test. And doesn't that then lead to like repetition? Doesn't this violate don't repeat yourself dry? Yes, exactly. And that's what I meant with test code is exactly the same as production code, but it follows different rules. In tests, it's more important to have stuff being easy to understand, readable, and to keep the reader of the test in your method than to stick to all of those principles you're used to. And if we see how we can improve this further, this is actually still bad, because what we now do is we delegated the creation of the web server to another class. But this is something you typically do in production code. Hey, you layer stuff. But this is actually super bad for testing code. Because how is the web service now created? You don't know. You have to jump into that method to figure out. Whereas if you just inline it, you can easily see, we create a new instance, and we just set the username and password in it. OK, fine. Now the test explains itself. Same for the assertion. Here we have a generic assertion, check login failed. But what does define a failed login? Is it that the result object has a particular subclass? Is the result null? Is there some parameter on the result which you can check? So inline this. And then you can simply see, OK, if the Boolean on the result is false, that means a failed test. Now this test keeps the reader in the test. You just have to look at the test and you know exactly what's going on. And again, this means repeating yourself. This is advocating for copy-paste development. And if your setup, part of your test, becomes too big, well, then you're copy-pasting a lot, right? But that actually is a sign of a weak architecture overall anyways. Plus, you can always extract the method which creates the web service for you, but then make it a method in the sense like create web service with username and password. If you then look at the method and you inject these two parameters in it, then from a test point of view, you could still understand what's going on without opening the method. So good tests keep the reader in the test. Let's have a look at this one. Well, here actually, again, multiple things are wrong, but for instance this, we have a comment in the test. Why would we add comments in the test? Comments are already a code smell as they are, except when they're documenting the why of things. But yeah, in the test, we shouldn't have that, right? It's not a public API anyway. So let's drop the comments. And then we're encapsulating our tests. We're using internal, private, and stuff like that. But it doesn't make any sense, right? It's just noise. Test classes don't reuse each other. You don't have to encapsulate test code. There's really no point in doing that. It's, again, one of those core fundamental principles that you're violating, right? Just remove them. Tests don't require that. And here, we actually extracted the width and height to a constant, which is quite costly in Kotlin because you have to write 4 lines of code in order to be able to do so. But if you look at the test, you don't know what's going on anymore. You don't know what is the width, what is the height. So it's better to inline those. Magic numbers and strings are perfectly fine for tests. Embrace them. Now, at least you can say like, we calculate the parameter of a rectangle with 5 and 10, and that should be 30. Everybody can understand this test. You don't need to leave the test to be able to understand what's going on. So remove all of the clutter as much as you possibly can. Last test. So what's wrong with this one? We're doing 2 asserts. What's going to happen with the second assert if the first one fails? Will it still be executed? No. If the first assert fails, the second one isn't going to be executed. And this test, even more, can fail for multiple reasons. Either the first fails, or the second fails, or both of them fail. So this also violates our concise test principle. So let's remove one assert. But this is not everything, because if you now look at this test, it's hard to read, because everything is aggregated together. Let's split it up in like an arrange, where we do the setup, an act, and an assert. That your tests have like a predictable structure. If you use that in all of your tests, then like the mental overhead of reading a test becomes a lot lower. And then lastly, this method. Imagine if this test fails, then the outputted error message would be logging has failed. Super vague, right? Wouldn't it be better to give it like a clear description? User is null when login fails. If this test now fails, you immediately know like, okay, that's the problem. So optimize your tests for failure. Now, let's summarize this. Tests actually follow different rules than production code. It's totally fine to repeat yourself. You should actually. Magic numbers and strings, embrace them. Encapsulation isn't required at all. You shouldn't layer your test classes. Long method names are perfectly fine. All of this, which are generally considered to be good principles for code, they don't apply for tests. So, tips. Imagine if you have an application and it has some kind of UI. How do you test the UI layer? Well, my answer to that is simple. You don't. What you can do is you can dumb down the UI so there's hardly any logic in it. This is now again a bit Android specific, but I think you catch the drift. So imagine if you have view models. So your view creates a view model. It passes the repository in the view model when it gets created. And then to get updates, the view model subscribes to an observable. In this case, it's called a live data. And that way it gets subscription events. Now, the view model we can completely test, right? It has no dependency on one of the native components, because the view is usually on Android a fragment or activity, stuff that you can't simply create yourself because the system has to do some orchestrating in the background for them to work correctly. But the view model, you can completely test. The repository, you can completely test. The live data, yeah, you're going to test it implicitly. And then the UI, yeah, if you structure your code in this way, what's left in the UI? The UI, do you really want to be testing, like if you call set progress on a progress bar, that actual progress is set? Does that really bring much value? You could just skip those UI tests in this case, right? And then if you use JUNIT, you'll notice that all of the assertions, they're super confusing. Every kind of assertion has like a different name. It's super hard to find them. There's also no type safety. So if you have a Boolean, you don't know which kind of assertions you can do at the Boolean, except going through all of them. Take a library like AssertJ. AssertJ can simply, you call assert that, you give it the object you want to do an assertion on, and then you actually assert something. So it's a predictable structure. Every kind of assertion follows the same structure. And you even get autocomplete. Because if your object is a Boolean, you're only going to get suggestions for is true, is false. If it's a string, you're also going to get suggestions for is null, is empty. So now the IDE can also help you. And AssertJ can do a hell of a lot more than that. It can assert that lists contain particular values, that string ends with stuff. There's like tons of assertions available. Plus you can even create your own. So I'm not necessarily saying that you must use AssertJ at all costs. I'm just saying don't use JUnit assertions. Look for some library that you like and then use that instead. Now, nesting mocks. This is also something that can often occur, right? That you have a mock that returns a mock that returns a mock. So here we have a user manager that returns a user. The user returns a configuration, and the configuration returns an age. And all we actually want to be testing is that the age is older than 21, because then we can show alcohol ads. Now, if you think about this, there's really no reason why the advertisement should get a user manager injected. So let's just kill that. So now it gets the user injected. But also for the user object, why are we putting values on the configuration part of it? Let's just flatten it and have the user return an age directly. This doesn't just make the tests a lot easier to read, but it's also a lot more friendly with refactoring. Because in the previous case, if you made a change to user configuration or user manager, then you could potentially break all of the tests that do this kind of setup. Whereas in this case, only the user class can break the test. So don't nest mocks. Another thing you often need is providing test data. And we already have a mocking framework in place, so why don't we return a mock and then just return mock values for every kind of method invocation? Sounds solid, right? Well, actually, this isn't a great idea. Because if you now add a new method or value to the user class, then, yeah, IntelliJ isn't smart enough to return a new when mock statement, right? So it's not going to be extended automatically. Similarly, if you remove a property, then it's not going to be removed here automatically. IntelliJ is smart enough to flag it, that this doesn't compile anymore, but you have to go to the class yourself to fix it. A better way, actually, is to just inflate the Pojo. It's just the Pojo, right? Doesn't matter to inflate the real one. So create a fake user data, and if you do it like this, if you would now remove the first name field, then it would be removed in all of the tests. Refactoring of the IDE now helps you. Same if you add a parameter, you can easily do that. Spies. Who here uses spies? That's actually a tricky thing to do. I don't know if you know that. But a spy is basically, a spy is like a mock, but if you invoke a method on it, it's still going to actually execute the actual code. A normal mock, you invoke some method on it and it doesn't do anything, right? A spy actually runs code, which is tricky because spies can have side effects. Assume that you write a test which does a login on like the spy of a web server. So we run the test, we invoke the login, we check that the return code is correct, and then it's going to actually go off and do the web server call, right? But yeah, the thread of the test is idle, so the test is just going to finish, say success. Then you're going to start running your second test, maybe your third, maybe your fourth. And at some point, the result of that login is going to come back. And when the result comes back, your app may blow up. And then you're going to see the failure in test number 5, which was actually caused by test number 1. And then you can even get stuff where the order of your tests starts to matter for them to succeed or not. So spies are really not a good idea. It's exactly the same reason why you shouldn't do singletons. Because if you use singletons, again, your tests could get stateful, and then you could link them together, and then suddenly maintenance becomes a nightmare. And what if you have dependencies that you have no control over? For instance, on Android, it's very convenient. You have a camera class, and the camera class only has static methods. So if you want to build an app that uses the camera, you cannot mock the camera class, except if you use a different framework. But there's actually a very simple trick you can do. You can just wrap the camera class. So that would look like this. You create a native camera, which actually wraps a camera object. We create exactly the same methods or similar methods, and then we just call them through to the actual thing that we cannot test it. This could also be done for final stuff, but yeah, for static is usually a bigger problem. And then you may say like, yeah, okay, that's fine and dandy, but I can't test this wrapper. No, you can't. And this is again a case like, do you really want to test something like this? It's just a pass-through, right? This is something you can accept as a team. You know that this code isn't tested. You keep it as simple as possible, and then you just live with it. So, should you test everything? No. What shouldn't you test? The UI layer, like views, fragments, activities, stuff like that, you shouldn't test, because it's just way too hard to do. If you're really serious about testing, like we are at Philips Hue, we do also do some integration tests on top of stuff and some transitions between screens, but that's not in our unit testing department. We really consider that to be a separate build step even. Handovers between threads, you shouldn't test that. I did it once. You can do it. It will take you a few days. The test will be super slow because you need to introduce weights. But yeah, the value you get out of it will be very minimal. I/O operations you shouldn't do, those dependency wrappers you shouldn't do. Basically any kind of integration with the operating system, like talking to sensors, cameras, and so on, you shouldn't really try to test those in the unit test. So, let's wrap things up. I really like this quote. We need to be as confident in the tests we code as we are in the code we test. Tests are really production code, but different rules apply. So repeating yourself, for instance, is not a problem. Awesome tests are fast, focused, and never flaky. Code coverage by itself is completely meaningless, except if you use it within the developer team itself. And not everything needs to be tested. I actually wrote a few interesting blog posts about these subjects, so if you want to know more about code coverage or how to write awesome unit tests, please do have a look. And then I still have some image credits. I didn't make the Lego images myself. And with that, that's it. Thank you very much for coming. Are there any questions, maybe? Yes?
When unit has become integration, how you divide the range of the this test is unit test and the test information?
Yeah. So the question is, when does a unit test become an integration test? So the way I look at it, for me, an integration test is something where we really test our app from slightly under the UI layer, because we don't want to test the UI, till really where we mock out our web service. So then you have a very big pile of classes between it. So then it's clear that that's an integration test, right? Because if you take it at a micro level, it becomes super fuzzy. Because, yeah, if you write a class, a test against a class which uses a string, is that an integration test? Because the string is also a class, right? You're reusing it. So there's actually a very interesting blog post about Kent Beck about this subject. But so I don't worry about it that much. Unit tests are stuff that runs super fast, and a lot of the times, an integration test, there you really test like a huge bulk of classes, yeah, in some CI or something. Is that clear? Okay. Any other questions? All right. Thank you very much. Have a great Devoxx.